announcements, and hopefully I'll remember to make them all. At this point, lesson 7 online homework is what's open for you to work on. That's the binomial distributions. And I believe, I don't remember when that's due. Do you remember? Okay, thanks. So lesson 7 online homework is due Wednesday by midnight. Thank you. We went through a fair number of examples of it in class. So, you know, if you missed part of the binomial stuff or you have questions on your online homework, I definitely would recommend you access the class videos for it. I did get numerous emails when I woke up on Saturday morning of from people the night before on the lesson 6 online homework. I always know when there's a due date because I wake up the next morning to a lot of emails. I go to bed really early because I'm just that sort of person. And you know what my response is, you know, please ask the questions that you have during class. Like, don't wait till the last minute to do your homework, because by the time you work that homework, we're already well into the next section. So that's not managing your time as efficiently as it could. And it also doesn't enable you to be able to come to class and ask any questions. Like, I'm not around on a Friday night in the evening. I'm usually, or very often, hopefully asleep by 8 o'clock because I've had a full week. So anyway, you know, I'm always happy to answer questions in class. So I definitely recommend you be sure that you ask them with sufficient time. The other comment is I handed out another worksheet on Friday, and I also made it available on the Moodle page. It is due this Friday. So please make sure you hand it in. Now, one comment, when I tell you that the worksheet is due by class time, if you're going to email it to me, you've got to email it to me by class time. A bunch of people sent it to me late on Friday afternoon, and by then I've already made the solutions visible. So it is a hard due date. I feel like I give you plenty of time to get them done. And of course, plenty of time to ask questions as well. Okay. My last announcement is next Monday, class is going to be Zoomed for everybody. I know that's not necessarily ideal for people, but I have to be in Atlanta, and I still want to teach the class. I don't want to have to cancel the class. So next Monday, we're all going to be Zooming. And on Thursday, when I send you my weekly class update, I'll have a reminder, I'll have the Zoom link, etc. Cool. Okay. Any questions, comments, or anything before we continue talking about lesson 8? Okay. Well then, cool. So here's the deal. If lesson 7 online homework is due, oh, thank you, Leo, for asking a question. There was a question for me to go over number 2 on the lesson 7 online homework. What I'm going to suggest to all of you is as follows. Make sure you look at it with sufficient time to ask questions. I'm more than happy to answer any and all questions. You've just got to ask them. So yeah, it's due Wednesday by midnight. So I'm going to share my screen. Oh, number 2, you're just going to kick yourself. Ready? I don't even have to write anything down, which is sweet. So we got a binomial experiment. Now notice your numbers are going to differ slightly, but the vibe of all of these is the same. Okay. So in my particular example, it consists of 11 trials. We're told the probability of success on a particular trial, and we want to know the probability of success on another trial. Well, can anyone chime in and say what they think? It's going to be the same. Good. In this case, the probability of success on every trial is 0.12. Remember, if it is a binomial experiment, the probability does not change from trial to trial because every trial is independent. So it was kind of a trick question, but really not meant to be. But people tend to look for things to be a bit more difficult. But the point is, the probability does not change from trial to trial. So in my particular instance, since the probability of success on trial 4 is 0.12, that's also going to be the probability of success for me on trial number 8. Yeah. 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 Leo, is that good? Okay. So there was a request for number 5 and then number 7. Now I'll talk about 7 for a second, but I did do number 8, which is just the same as number 7. It's just a physics test as opposed to defective manufacturing, but I'm happy to talk about it. So question number 5. What do we have here? We have Delta Airlines flights from Chicago to Dallas are on time 70% of the time. Suppose 13 flights are randomly selected and the number of on-time flights are recorded. So what I want to make a comment here is within all of this right now, we have our N and we have our P. Okay, what is my N value? What's the total number of flights we're talking about being randomly selected here? 13. And we're given our P. What's our P value here? 70%. So we're going to enter that as 0.7 in decimal form. Okay, so here we first want to find the probability that at least 8 flights are on time. Okay, what does it mean for at least 8 flights are on time? It means 8 or more. Y'all with me there? Okay, now, if you have your notes out from how we do these binomial computations in our calculator, when we have at least, that's when we have to find the probability of the complement. Remember, our calculators can only do at most. Y'all with me here? So the complement of at least 8 is at most 7. So what you're going to do is you're going to compute binom CDF. You enter your N, your N, your P, and your X. And you're going to compute that, and then you're going to take 1 minus that value. Riley, is this okay? Now, for the at most 8 flights, cool. For the at most 8 flights, that's pretty sweet. We can just enter it, right? That means it's just a binom CDF, Again, your N doesn't change, your P doesn't change, and in this case, we want at most 8, so you enter 8. Yeah, I got 0.7 from the 70%.
No, sorry, the one above the 7, so you see how you put the 8 on this one that we're doing right now.
Yeah.
So,
Oh, okay. So why do I have 7 here? Yeah, that's a great question to ask. I'm gonna have to change my mode of displaying here. The reason why is, don't we want 8 or more? Isn't that what at least 8 means? Okay, well, the thing is your calculator doesn't compute some number or more. What it does is it computes at most. So what's the complement of 8 or more? I claim it's 7 or less. And so that's why I have right here, do you agree that if I want to find the probability of 7 or less, that would be my binom CDF, and then I'd have a 7 here? But then we want the complement of that. So whatever you get here, you take 1 minus that value. No, thank you for asking. I'm sure the rest of the class appreciates your question. No, seriously. And then finally, for the last one, we want exactly 5 flights. So what function do we use here? Binom PDF. And then you enter 13, 0.7, and in this case, 5. Once you figure out what buttons to push on your calculator, I claim this is just really a calculator section. I mean, the only stuff there really is to understand here is what makes something a binomial experiment. And we went through those 3 things in class. So for number 7, what I'll go through and talk about each of these parts, but what I will do is I'm going to steer you to the class video for number 8, because it's exactly the same thing. It's just the story's different and the numbers are slightly different, but I'm totally down with doing this. So here we're talking about physics students having a certain probability of passing their final. God, this problem makes people feel bad just from the start of it, right? So notice there's a 45% chance of them passing their physics final. And so that's our P. So we know P is equal to 0.45, at least in my particular example. And notice that there's 145 students in total that they're looking at. Cool. So what is the correct wording for our random variable? That's our X value. And that is the number of 145 randomly selected students that pass their physics final. And we already just saw that our N is 145 and our P is 0.45. So for this first one, we want exactly 59. So what would be our function there? Wouldn't it be binomial PDF? Yeah. And here again, with exactly, you're going to have a binomial PDF. Were there specific parts you wanted me to do?
It was this.
Are you sure? Okay, yeah,
I
Michael?
know that I got them all right. It said
Oh, okay, because the less than and more than, when we went through these, and I'm happy to go through E and F. That's awesome. Okay, you have to note that those don't include that value of 59. So these are a little trickier, just the parts E and F. But let me show you. So part E, we want to find the probability that less than 59 pass their physics final. Okay, what is less than 59? Are we counting the number 59? No, good. So in that situation, what we would do is we would use binom CDF. And in this case, I'd enter my N, my P. And so if we're not counting 59, that means we're interested in 58 or fewer.
So you still don't subtract the one.
No, you don't subtract the one in front because you're still doing less than. Now, look at this one though, but how about more than 59? What does more than 59 mean? Not a rhetorical question. Doesn't it mean 60 or more? Okay. So we can't do the or more in our calculator. So that's when we have to do the 1 minus. But notice here, you don't have to subtract 1 from that number because there's a difference between saying less than 59 versus at most 59. So in this case, the way you would do part F is, yes, you would have to do the 1 minus because whenever it's more than or at least, you're going to have to do that 1 minus. N, P, and in this case, if it's just the strictly less than, you can keep that number the same. Thanks, Michael, for asking that question. Excuse me? Yes. Well, no, this one was for more than, this guy was for less than. And what I will steer you to do is please see the video that I did on Friday. So Riley, 13 trials, 80%, exactly 2 flights are on time. Okay, so what I'm going to do is I'm going to stop sharing my screen here. Okay, so now I can. So what I have here today is this TI calculator. Do you see it? So you're going to go down to, since it's exactly 2 flights, we're going to do binomial PDF. You said your N was 13, your P is 0.8, and you want exactly 2 flights being on time? All right. So notice we got 1.0223616 E -6. My guess is that the online computer program probably wants you to put that as a decimal instead of in this scientific notation. So recall what this E -6 means is that in order to write this in a decimal, not in scientific notation, so you got to move your decimal 0.6 places to the left. So you'd have there you go. So essentially you got to put 5 zeros in front of it. So see if your if the program accepts that, Riley. Yay, cool. I love when things work. Don't you? Well, thank you all for asking the questions that you asked. I think it's really important that you ask questions, and I just want to keep encouraging you to do so. All right, so what I want to remind you of is we were talking in lesson 8, and what we were making were those probability distribution tables. You remember that? And what that did is it helped us organize all the possible outcomes that can happen with their associated probability. Okay. So we're going to piggyback to those momentarily, but you may or may not recall then at the end of class on Friday, I asked you, how do you find the average of, say, 3 test scores? Y'all kind of sort of remember this? I'm sure you thought of nothing else over the entire weekend, right? Yeah. Okay, cool. What'd you do? If you have 3 tests, how do you find your test average? You add them up and you divide by 3. Okay. So what I'm about to do right now is I'm about to motivate how we find the average of a probability distribution table. Okay. So what I'm going to say to you right now is you don't need to write this part down if you don't want to. I will tell you when you want to start taking notes. If it helps you to take notes all along, then, don't let me stand in your way. But right now, what I'm doing is I'm just going to motivate where a formula comes from. I know that some people like to just be told formulas and they trust that it makes sense. I was never that sort of person. And I always like knowing where things come from, because then it lends meaning to the computations that I'm actually doing. You are never responsible for deriving formulas. That's beyond the scope of the class. Okay, so most important is if you can follow my steps, please chime in and ask questions if you have questions while I'm doing it. Okay, those of you on Zoom, please do, and those of you here as well, please do. So what I'm going to do is I'm going to make up some silly scenario, and I'm going to define my random variable X to be, oops, I don't want number in front. I want it to be the average number of hours of TV watched per day. Okay. Now what I'm going to start out making is not a probability distribution table. It's a frequency table. We've seen frequency tables before, like when we were making just the table of, favorite hobbies, number of people who like to ski the best, or read, or draw, or sing, So, but I'm going to make it a horizontal table as opposed to a vertical table. So suppose I did this survey and the values that I got is that on average, some people said they watch 0 hours of TV per day, 1 hour of TV, 2 hours, 3 hours, or 4 hours of TV per day. And it turns out that 7 people that I queried said they don't watch on average any hours of TV per day. Okay. 12 people said they watch on average 1 hour of TV. 4 said 2 hours of TV on average. 3 said 3 hours on average, and 4 said 4 hours on average. I made up these numbers. Okay. Like this is not some deep scientific study here. Okay. So what if I asked us to find amongst these people that we queried the average number of hours from this group? Could we find the average here? Thank you. We totally can. Okay. How do we do that? Well, 7 people said 0. So if we wanted to do this really long drawn out, we'd have 0, right? 0 plus 0 plus 0 plus 0. We wouldn't really do that. But isn't repeated addition the same thing as multiplication? Okay, so we're going to use that idea because that's ultimately where multiplication comes from. Okay, so in other words, we have 0 and that happens 7 times. Now we could take 1 and add it to itself 12 times, but it's simpler just to say, well, that's 1 times 12. We could take 2 and add it to itself 4 times, but it's shorter to write 2 times 4. So plus 3 times 3 and plus 4 times 4. What do I divide this by? I was hoping someone would say that. There are 5 different values that we have, but we have to remember we're doing repeated addition. We have to divide it by the total number of people here. And what's the total number of people? 30. You're awesome. So we actually have to divide it by 30. Okay, so it's a difference because we're doing this repeated multiplication. So not that we really care, but it turns out that it is about 1.5 hours on average. Do we care? No. But are there questions this far? So this is just simply using the idea of finding average. Okay, now check this out. You ready? See this up here? What I'm going to do is I'm going to kind of just do some arithmetic, but I'm going to go backwards and it's going to seem really stupid what I'm doing, but I swear I'm like going somewhere with this. Do you agree in general, what you try to do is take a bunch of fractions and put them over a common denominator? We can break this up into 5 different fractions if we wanted to, though. So do you agree, at least mathematically, it's equivalent to saying 0 times 7 over 30 plus 1 times 12 over 30 plus 2 times 4 over 30 plus 3 times 3 over 30 plus 4 times 4 over 30. What I did is I just broke these up into 5 different fractions. Seemingly, it looks like I'm going backwards. Any questions about that mathematically? Now, the next thing I'm going to do is going to seem just as backwards. It's a great way to start a Monday, isn't it? Okay, what I'm going to do now is, and this is just arithmetic that I'm doing. Okay, I'm going to pull out this number in front. I'm going to say that's equivalent to 0 times 7 over 30 plus 1 times 12 over 30 plus 2 times 4 over 30. Now, if you're wondering why in the heck I'm doing this, just be patient with me. What I need you to see is that what I have written here is equivalent to what I have written on the line up above. Okay, why is it equivalent? Well, when you're multiplying 2 quote unquote fractions, you're just multiplying the numerators and multiplying the denominators. So you're still going to get 2 times 4 over 30. We just brought it out in front. All right, you still don't need to write anything down. But what I'm going to do now is I'm going to rewrite that frequency table we had on the previous sheet. But now what I want to do is I'm going to add an extra row to this table. I'm going to change it from a frequency table to a probability distribution table? So let me ask you this. What's the total number of people we're looking at? 30, okay? So we know that 7 people answered that on average, they watch no TV per day. So what if I told you of these 30 people, what is the probability that a randomly selected person said that they watched no hours of TV per day? 7 divided by 30, beautiful, right? You take the number of ways it can happen divided by the total. What's the probability that a randomly selected person said that they watch on average 1 hour of TV per day? 12 over 30. Okay, how about 2 hours of TV per day? 4 over 30. What do I put here? 3 over 30 and then 4 over 30. Notice if you add up your probabilities, you get 30 over 30, which is 1. Life checks out. Okay? You with me this far? Now, notice when we wanted to find the average, this was the computation that we did. Okay? And let's compare things. I have 0 times 7 over 30. Isn't that this X value times its corresponding probability? And then I'm adding it to, oh my goodness, this X value times its corresponding probability, plus this X value times its corresponding probability, on down the line. So what that gives us is a way to compute the mean or the expected value given a probability distribution table. So if you haven't started writing yet, now you want to, assuming you take notes in the first place. So to find the mean or the expected value given a probability distribution table, literally what you do is you take, here, let me put a comma here, take each X value, multiply it by its corresponding probability, and add them up. Now we saw that the average that we got was 1.5. Notice 1.5 was not one of our X values on the table. But if you may recall, when we took the average of those 3 test scores on Friday, we didn't actually get one of the exact test scores. Okay, so it's not uncommon. Okay, now I want you to note again that we got about 1.5 up here, and notice that it makes sense, right? Isn't the highest probability 12 over 30? And then we have 7 over 30 bringing it less than 1. But then we also have what, 11 over 30 making it larger. So there's a strong pull here because this is the highest probability, but there's more on the upper end offsetting it, which is going to bring it a bit higher. Okay. So I'm just asking myself, does that answer make sense? So this is it written out in English. What I'm going to say is there's an associated formula. Do you have to memorize the formula? No, you just need to know when and how to use it. Okay. And if you prefer it written in English, then you don't have to write this down mathematically. But notice, to find it, what you do Notice it's the expected value, so we call that E of X because we're not original folks, okay? You take each X value times its corresponding probability and add them up. So I'm going to take my first X value times its corresponding probability and add that to my second X value times its corresponding probability. And go on down the line until you've gone through your entire probability distribution table. You with me there? All right. So going back to an example that we did on Friday, may I? So this is what you need to know. And how do you know to use this formula? You see the word expected. It's kind of a dead giveaway here. Do you remember we were playing with this example about having a bag of a total of 2 purple marbles and 4 blue marbles, and we wanted to make a probability distribution table of counting the number of purple marbles picked out of the bag? Do you remember this from Friday? And we went through and did this. Well, going back to that previous table, again, this is in your notes from Friday. What if I wanted you then to find the expected number of purple marbles selected? Now, you may or may not recall that one of the things that I talked about at the very end was noticing, oh my goodness, check this out. This has the highest probability, right? Where is it weighed to from 1 purple marble? More towards 0 or more toward 2? Zero, right? Isn't 6/15 a heck of a lot more than 1/15? Okay, so just by looking at these values here and where the probabilities lie, I'm thinking it's going to be between 0 and 1, but a heck of a lot closer to 1, just because this is what's got the heavier probability. But we can compute it. You take each X value times the corresponding probability and add them up. Now you can do this by hand or you can do it on a calculator. No matter what calculator you have, the beautiful thing is your calculator knows its order of operations. So you can enter things as one long strand. And you don't have to put 0 times this. Why not? Because it's always 0, right? 0 times anything is 0. But if you want to put everything just to be sure, you can literally type in 0 times 6 divided by 15 plus 1 times 8 divided by 15 plus 2 times 1 divided by 15. And we're going to get about 0.67. Now, can you get 2/3 of a marble? No. But again, remember with our test scores, our average wasn't one of the actual test scores either. And notice this makes sense to where the probabilities were really weighing heavily, right? We saw that it was most heavy at 1, but 0 was pushing it down a bit. All right. So what I'm going to do now is as follows. Well, actually, what I'm really gonna do now is I'm going to say that tomorrow in class, I'm going to go through several examples for these probability distribution tables and what you should expect to see. Tomorrow's examples are very similar to ones you're gonna see on your homework, ones you're gonna see on your class activity, and ones that you would see on your test. Okay, in other words, if you're not gonna be in class tomorrow, you wanna catch the recording, but we're gonna talk about life insurance policies, and we're gonna talk about raffles and all sorts of really fun things like that. Cool. All right, if you need, if you're here and you want any of your, if you've handed in anything physically, I have everything to hand back. I'd love to hand stuff back to you. Have an awesome day, everyone.